Hello, everyone. So I'm Mateos. I'm the current chair of IEEE Computer Society here at USF. Um, uh, Today I want to talk about, give you a presentation, hopefully introduction to what is computer hardware, from the most basic beginnings, from what is a computer, all the way to more newer more complex topics. So that way you all can be aware of everything regards to hardware, computer hardware, which is I think is very important for all that department, computer science engineering, and maybe other people too. So and then also I mentioned there Brooks only because this presentation we did a year ago, and some of the content was also created by him. Okay. And any moment you have questions, just let me know. I can also have a Q&A at the end. So first of all, who I am. So it's not a random person. So I'm a I'm a computer engineer. I'm doing my master's here at USF. I also did this before. I'm currently doing a thesis on monitoring and controlling eye fluid pressure for machine learning. My current professor is Dr. Robert Karam, also who is the advisor of the club, and also applying for PhD starting next semester. I have done 3 publications on hardware security, about implantable robotics, and more publication there on. And then I also have teaching experience. I'm currently a TA for Computer Architecture Lab. You might be familiar with that. And then computer organization and practical hardware security the previous semesters. And also I used to be a tutor at the Engineering Tutor Center, also the manager there. So you might see a lot of my content over there, like the logo, for example. So that's all about me. Now actually get into the actual content. So we are going to talk about a little what is computer, computation, computer hardware and software, while learning computer hardware from computer scientist and computer engineer perspective. What is the generic computer hierarchy and components, analog versus digital circuits, types of hardware computing technologies, memory and storage, and the future direction. So I'm going to quickly go very surface level overview of what neuromorphic computing, maybe you heard machine learning, and then quantum computing. Okay. So overview. So what is a computer? Well, it's any any device that performs computations. So it could be electrical, mechanical. However, in the past, computers used to be people. Okay. So in the past, they used to have a group of bunch of females. Okay, like for example, this famous researcher called Catherine Johnson. Um, so they will have a room full of females, and they will be going through the algorithm and doing the computations on calculators and so on. And you have like some random guy come in with the algorithm and say, hey, do this computation, and basically they were the calculator side. So they're very smart, okay? And even she helped with getting the um, um, she helped with one of the project of NASA to get one of the many rockets somewhere. I forgot where it is. But not only that, now computations. What kind of computations? Well, the action of mathematical computations. So it doesn't have to be specifically a computer like this. It's any device. It can be something like a very small circuit, as long as it's doing a computation, like addition, subtraction. So numeric operation, including data manipulation, storage, interpretation, algorithm, execution, number system modeling, anything with numbers, okay? Now, there are 2 ways how we can implement this, in hardware and software, okay? So first of all, what is computer hardware? Well, the computer hardware is the physical, concrete, okay, the tangential part that the component of the computer system requires to function, such as monitor, mouse, keyboard, processor, memory, so on, all the physical parts. You cannot do anything without the computer hardware. What is software? Well, it's the virtual, abstract. It doesn't exist. It's imaginary. We fool you using computer hardware to fool you seeing buttons and like you can see, hey, there's a computer. No, this is just LEDs coming from there, just light. So of interpretation, what the computer system is doing. So instead of you having to analyze what the circuit is actually doing, you can get like an easier view of what's going on the screen, even though it's just bunches of LEDs turning on and off. So example, program, application, operation system, firmware, etc., etc., etc. So what is the difference? Well, virtual is software. Hardware is physical. The software is instruction code. Hardware, we're talking about circuits, materials like semiconductors, transistors. Software, not required for a computer, so you don't need software in a computer. You can just have the computation going on, but not software. But hardware is required, so you cannot have software by itself without hardware. It has to be running on something. If damaged, you can use backup copy. But however, if your hardware is damaged, you have to buy a new one. That's the sad part currently. Unless we can somehow fix it easily, but you have to buy the new components, that buy the parts, or the entire system. Bugs can be fixed easily, and features added. And then, however, in hardware, bugs cannot typically be fixed because you have to fix the circuit. You have to change the circuit. And once it's already produced, then you have to produce a new one. For the same reason that if it's damaged, you have to buy a new one. Generally, software are serial temporal computing, while hardware is parallel spatial computing. Now, these two new words, what do they mean? Well, actually, four of them. What do these keywords mean? Well, hello, daily bug out? Oh, stuck for some reason. Oh, Akira, this is stop working. So I can just use don't worry. Yeah, okay. I just want to point. So serial, temporal, what it means is basically goes step by step, one by one. Okay, it doesn't run all the instructions at the same time, and you can see it's time dependent. So you cannot do everything in the same time cycle. You have to do one, then the other, then the other, then the other. So here's an example of how to compute a like the quadratic equation. So ax squared bx plus c. Okay, all those are given constants. We just want to compute y. But in the CPU, you have to load the x, then you multiply the x loading this register times a, which gives you that. Can you move the thing? Can you move this? Thank you. That's the Could you that's the wrong. Now? Yeah, but that's the wrong slide. Yes. Thank you.
IT support.
Nope. Up, bugged out. Oh, ignorant. So then we can add a b, then multiply, and then do another addition for the c. So you can see it took 5 times. Okay, 5 times units. It depends on how fast the CPU or the device, but you can see it would take 5 steps. However, in hardware side, you can do more parallelism. So you can do like some computation at the same time. So for example, you can do this multiplication at the same time of this multiplication, and then this multiplication at the same time of that addition, and then this final addition to get the final computation. So you can see for this simple operation only took 3. And if you want to think of it like in the long term, if you're going to do multiple of these operations many times, eventually this save of 2 times units is safe a lot. Also, not only that, in CPU, normally this is based on a clock. And however, this doesn't wait on a clock. As soon as the data is out, you have it immediately available and you can just use it. You can use immediately available. However, here, this might be already available, but you have to wait until the clock. So there might be some additional waste. So this is the idea of, hey, maybe we can use some hardware to help computers too. So another reason why hardware is important. Now, why learn computer hardware? Well, if you're a user, okay, it helps with understanding the limitations and capability of the device. So if you know how the computer works fully, you know how to use it at the best of your advantages. Custom and build your own computer if you're interested in that. You can write, from the programming perspective, you can write better programs, okay? So use less data less data and memory, more efficient use of resources. So you don't want to like constantly checking the memory every time if you can load it at once, things like that, or use incorrect or use the same resources for two things and accidentally make a bug. Those are important. Work with embedded system and Internet of Things, IoT. Those are like chips, so you can use it to build, like for example, build mobile robots. You can use it to also build system sensors like home security, temperature control, monitor detection, medical wearable or implantable devices like glucose sensors, so on. So this is still hardware level. It still has some programs that you can still execute, but also at the same time it has hardware connected so that we can do certain specific tasks without taking too much of the CPU usage. And then create new and so for the hardware, the computer engineer perspective, it will be create new and improve hardware circuit. So provide alternative or better solution to in the circuit level. So maybe there's already a solution in the software, maybe like a machine learning system, but that's in software. Maybe we can propose a hardware level that's much more faster, okay? Because you can add the parallelism to it. The CPU doesn't. And then also analyze power area performance, PPA. If you see me using the word PPA a lot, I'm talking about power area performance to trade-offs. So you can, hey, do I care more about area? Do I care about more speed? Do I care more about power consumption? Things like that to make a more efficient hardware, okay? Any questions so far? If I talk too fast, let me know. So let's talk about what is the genetic computer component. So I created this years centers ago. So basically, you can think of the computers like hierarchical, like the abstractions. You can abstractly visualize it like that. Of course, the computer architecture is like computer itself is one chip, but in our head, we can distribute the task in this way. For example, the top level, it will be what you see from the user perspective, the screen. You're not actually seeing what the circuit is going on. But underneath that, we can add, for example, the applications, the program, what is the code running that. And then there's, sorry, the application itself, and then underneath that will be the program. So um, the C code, the Python, whatever it's doing to execute the program. Then underneath that, there's the compiler and firmware. So it's managing, so the compiler is converting this code into assembly code that is more closer to what is going on. And the firmware is just making sure other like more security measurements and other things. It does some other tasks to make sure everything's doing well. Um, then assembly language is like another language, but it's more closer to what's going on in the circuit. Um, but however, this is still written in English terms in like alphabetical letters. So, but the machine doesn't use that, use binary, like ones and zeros. So the machine, so there's an assembler that will convert one to one that information into ones and zeros. That, and then that technically gets loaded into the ISA. Now, there's like one step here operation system. It's the lowest level of the software. The OS manages that all this software and make sure it also is managing communicating with the hardware level. So that way, make sure everything is secured correctly. So the OS is doing like it's a special program that's doing like all the work. Make sure your computer is running well, you run the correct programs when you want to, not running when you don't want to, and so on. And then under here, we have the actual physical component. So we have here the processor, the inputs and output, memory. Underneath that, you can go more into the more of the control system and path. So how the wiring connecting, how you connect the modules. And then underneath that, we have digital logic circuit. So each module uses the most basic computer circuit. We call it gates. Also, you can use more complex like ASIC circuits. We can touch more in that. And then underneath that, each logic gate are built mostly in transistors. So basically, almost all computer circuits are basically just a bunch of transistors. We rarely use resistors. We rarely use inductors because I can touch more into that why. But basically, it's more into the analog level that I can mention that. And of course, we also want to, when you're working more in transistor level, you also want to consider what kind of material, what kind of molecule, what kind of atoms, how all the, you still, that's why we also take chemistry a little bit to make sure we understand this. Like, what is the best semiconductor or something like that. Now you know like how we distribute the roles. Like someone else can be just doing this, someone else can be doing just that. Then stop working again. I don't know what you done. Oh, thank you. I think because I'm hitting the top button and that messes up. Anyway, so more standard components. You're gonna see every single computer. Oh, sorry, not computer, but of a PC, personal computer. So this, and also laptops also has something. So of course, a motherboard. You need like a PCB where it holds all the components, and you have additional circuit. On that PCB, you have the CPU, which often is in the middle. It's like well, this time it's over there, maybe to dissipate a bit more of the heat. Okay, the RAM is the temporarily memory just to run the program, but once you turn it off, this is gone. Interconnected bus that basically wires that connecting everything together, and then interface like inputs and outputs. So like an antenna, for example, that you can receive data, or you can have like a port somewhere that you can connect more pins. Now this is the minimum in it, but we can add more into having additional storage, because remember to say that RAM forgets its memory. So you want an additional storage to make sure to keep it up. The reason we just don't use this because it's very slow. Okay. We just use it for temporary. You can even add additional external, like an external SSD, like you just connect with USB, wireless connector adapter, like that. If you want to connect to Wi-Fi instead of wirelessly, instead of with circuit, like sorry, cables into the Ethernet cable. Video graphic card. This is not required, but it's technically going to improve significantly. Almost every single computer nowadays has a video card, because otherwise it will have to compute pixel by pixel. Graphic card can make it more better, and you can use it for other things that we can touch about. If you're wondering what GPU is, it's an image processor of video and graphics. Okay, and I'm gonna talk about it soon. Hey, can you check in over there? Yeah, and then you can grab food if you want some. So what's the difference between analog and digital? Okay, so analog circuits. So the main thing is how we define a signal in computers or any circuit. We care more about what is the voltage value. Okay, so over time. So what is the current voltage value? So commonly, analog is continuous. You see, is you can any of these values are valid, are acceptable for analog. However, digital is discrete. You can see either I only do like low voltage or high voltage. Okay, 5. So anything in between is not acceptable. Okay, so it has to be a specific set of numbers. It doesn't have an infinite range. While here is any range. Okay, um, so commonly this is used for like mostly signal processing from sensors like temperature, sound, light, like because those are like changes over time. However, in the computer, we use it for binary. Like you can see how I represent like low is 0, this is my high is 1. So if you see 0 and 1, that's what normally means underneath the circuit. Low voltage, high voltage. You use it for computation, data storage, manipulation, so on. Because if you want to think about it, okay, let's say I have some data here. I want to store this information. You cannot just store it in analog circuit. There's no such thing as memory, analog memory. You have to bring it to digital, and then you can bring it back. So you can do back and forward. Analog is sensitive to physical environment. Okay, noise, because any of this is important. However, if there's some noise here, at least it's like high enough to consider it high. So the noise is not that important. Um, it's still important in certain cases, but normally it's not. And this normally is asynchronously. That means it doesn't depend, like use the data as it gets it, it uses it. However, this is synchronous mostly. It means it mostly depend on a clock. Okay, so that way it cannot do the next instruction or the next information. It has to wait for the clock, and then once the clock say now go, it does the next one. Um, Often analog electrical engineers does more analog, and computer engineer does more um, digital logic. But we constantly swap out back and forward. For example, I'm looking at maybe I can use analog to speed up the digital and digital to help with analog, so on. They have always benefits, but this is normally what we have. So a little more analog. So remember I mentioned that they are convertible, so you can convert back and forward. Um, um, so for example, you can have mixed signals in the circuit, as I was mentioning. You don't have to be purely digital, purely analog. You can have a combination of both. So what is the purpose of this? To improve cost. So power, area, speed, performance, memory, money, so on. Maybe purely hardware might be much more complicated to use and doesn't cannot do all computations. So, but it can do certain things very, very well at very low cost. So you can add that and maybe improve certain things. So for example, this is an example how it gets converted. So you can have that sound comes in analog signal, then we make it discrete. So we grab certain points. Let's say this is your sound. We grab certain points and we make it discrete. You're gonna see that it's not necessarily have to be just 1 and 0, but you can see it has certain specific numbers, okay? We can store the information coded in binary and then store it in the computer. Okay, now you run this. I would just rather if you don't touch it too much. Okay, so but you're gonna see that I was mentioning that you can have multiple values. So if I only have 0 and 1, how can I encode more numbers? Well, you just add more digits, like similar. So that's where binary come from, okay? So maybe you're familiar with digital. Okay, you have decimal, 0 to 9. That's all your decimals you have. And then once you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, you run out of digits. What we normally do, add one more digit, and so on. So you do then 0, 1, 2, 3, 4, 5, also on. Similar with binary, but you only have two digits, 0 and 1. So you start with 0, then 1, around another digit. So I put another decimal. And then I can do 1, 1, around another decimal. So I add another decimal here, and so on. It's the same way as counting up. It's the exact same way. It's just you have less numbers to use. And you can see eventually this kind of grows faster than number digits. But that's the only way we can use it now. Now, well, I've been saying a digit, but in reality, we call it a bit. That's a binary digit. So every time you hear me say a bit, I'm talking about one of those numbers. So this, for example, is a 4 bits number. Okay. Now, why bits? Well, normally it's because most digital circuits and memory are only have two possible states. So those states can be configured many ways. It can represent anything, but we label one of them as it means high, and this is if it's low, even though they look like you can flip it upside down and look the same. Um, so, for example, in the case of memory, you have high and low. So here's an example memory bus, and you can see currently storing 1010. What is the number? Well, let's check the table. Oop, I lost it. Okay, 1010 is 10. You see? So 8 plus 2 is 10. There's techniques how you can do that another way, but I'm not going to go more in depth in that. But just to show an example, the normally a memory has a write enable. So you need to enable it. You can read it at any time, but it doesn't write anything. So if I put some content here, like that, let's say 7, still doesn't change the value. It still is waiting there. But once I turn on, look at once I turn on the 1, you can see now it changed the content. So but regardless, it's still binary, and each of the memory cells can store one of those bits. Okay. Any questions so far? So types of computing technologies. Okay. So we have a lot of different type of computer technologies. So the most familiar that you are is software specifically processing, such as CPUs, processors, GPU, microcontrollers. Most of you are familiar with that. Those are like the ones inside these computers, these devices. However, that's not the only type of computing technology. We also have what is called application-specific hardware, so chips that does one specific task. Okay, like very good at multiplication, very good at addition, very good at something, but you cannot put a program and do whatever you want. That's the case of software. You can put a program and do whatever task you want, up to the limitations of the computer, of course. And then there's reprogrammable hardware, which basically, in this case, you cannot change the circuit, but here you can change the circuit. Okay. So for a couple examples, this one we have ASIC, and then for this one we have FPGA. I'm gonna get more in depth later. So for software processing, we have we have a CPU. This is how normally CPU, the most abstract version you're gonna see. So you have some inputs, some outputs, then the CPU, and then that's connected to the memory. And you can see that memory only has one path. So if you wanna get, the memory has all the instructions, all the data, but you can only pass back and forward one at a time. You cannot pass all of them or multiple of them. So that's why computers does one instruction at a time, one data at a time. And this single path, this architecture, we call it the von Neumann architecture, because that's the person who came up with this idea. But this causes a minor issue that you have to wait, like you cannot send two data at the time, only one. That's what we call the von Neumann bottleneck. Okay, that's the limitation. So alternative name, we call it general purpose processing unit. In reality, most computers nowadays just don't have a central processing. We now have what is multiprocessors, so they don't have a central one. They might have multiple of them, okay, to speed up. So that's why we just go to general purpose. That's what they do, anything. CPU feature has a memory. Okay, also inside has registers. Okay, register stores temporary memory just to do the computation much faster than having to load back and forward the memory. You can just temporary store it there without having to go back and forward with memory. This is going to memory is very expensive, but registers are not in terms of speed. You have a control unit that controls the CPU, like what to do, when to do it, things like that. And then an arithmetic logic unit, which does the math, like addition, multiplication, division. This is the main circuit that does that computation in computers. Okay. And this is what I was saying, that there's not such thing as CPU. There are multiple processors. Or you may see also the word cores. Cores processors kind of become interchangeable nowadays, even though they have a specific purpose. Okay, they have a specific name. So, for example, only this is a core. Raspberry Pi is another general purpose computer. Now, what is a GPU? Can someone tell me what is a GPU? What is inside? One CPU? Yeah, so it basically it's many CPUs. So it's an array of arrays of arrays of CPUs. So you can have a CPU with a microprocessor, and that microprocessor has 32 cores, and that way each of those cores are actually just are very small. They don't do a lot. They only do like very basic addition, multiplication. So often it's just that, or other things too. But just try to limit that as much as possible, because if you put very heavy circuit, it's gonna overheat and burn it out. That's why you see GPUs, like this is a GPU board, and then on top of that, it will have a very huge fan to cool it down, because this overheats a lot. And even with that small thing, you can do that. But what is the benefit? For graphics, instead of having a CPU doing one pixel at a time, you can have the GPU do a block, a chunk of many pixels at the same time. And this is redirected to from the memory. It doesn't have to go through the CPU. That way, the CPU does other tasks while the GPU doesn't. Hey, can you also sign up there? Let's get. That's our treasure, by the way. um, Now, a specific graphic. Now, not only for graphics, but you can say many CPUs. There are still many general purpose CPUs. So you can also do multiple computation. Like say you want to do matrix multiplication. Either you have the CPU do one of the elements at a time, or you have the CPU, or you have a GPU that does multiple then at the same time. So that's why it's very good for machine learning, because it does a lot of matrix multiplication and additions. Okay. Any questions so far? Yeah. So what is microcontrollers? You may be hearing the term. A lot of people think it's just a CPU, but it's actually a bit slightly different. Think of it as a smaller computer, like a smaller CPU. It has memory for storing the program. So the program itself is like in a flash. Okay, it's much more smaller. It's not like it's not an SSD or hard drive in the same way as you have in a computer. It's something much like just a tiny chip. Okay, just for the instruction, and maybe another one for the data, but it's very small. Also, not only that, they're often what we call system on chips. Not that not only has the processor, but also have all the components in there. So that way you save space. So for example, you can have the the this is called the analog to digital converters, the CPU, the RAM, counters, memory. This is UART, basically how you communicate between this chip and the USB. So you can transfer back and forth. Then all that, instead of being separately, as in the computer, just all in the same chip. Okay, often are like that, but they're very micro. So just a chip, that's all it has. Okay, and they're very small. They don't have that much memory, and they're well suited for low power consumption. If you want to do the same thing in circuit, you can do it like that. Such as an Arduino. Okay, that's one very famous example. Not only that, you can use it for also communicating. It's easier to make it communicate with additional circuits because very simplistic compared to a higher CPU like a Raspberry Pi with an OS in there. You have to like manipulate the OS of how to understand there's additional circuit. Cheaper to mass produce because you don't have the expensive parts. And STM32 is another example of a microcontroller. Now, ASIC. What is now we are getting outside of software processing specific devices. This is more circuit level. Now let's design circuit. But if you design a circuit, okay, once they are specifically for that particular task. So circuit for one purpose, okay, that's very important. You can technically get away with maybe two purposes, but in reality, it has one purpose that just has two tasks inside, but it has a general purpose. Okay, circuit relies the target application. So you have one task you want to do, you can do that and very, very well. Okay, that's like a lower power than general purpose hardware because you don't have additional stuff to do like get instruction. What should I do? What to do? Decode that and then all that. It just doesn't. Okay, it's like imagine that like what it needs to do is there and doesn't need to think about it. So here's an example. This is an example I did from a course here at USF called CMOD VLSI, which is transistor level with Dr. Kakuri. And basically the task was to create a 16 by 16 bit multiplier. Well, it was 8 by 8, but I did 16. So this thing, if you zoom in, here is what we call an inverter. You can see I had to draw those rectangles one by one for all of them. Well, I kind of copy paste the repeating ones. But imagine if you get the ground size, the ground dimension, all that will take time. So even though they're very cheap to mass produce, they take time to produce. Okay, so to design. So this is where we get some limitations. So CPU runs software code. ASIC hardware circuit programs in a sense, like the task. It's not actual software. Serial operations, you can kind of get some parallelism with GPU, sorry, with multiprocessing, but it still can only get from the main memory one by one. However, ASIC, you can have it whatever you want. Serial parallelism, you can fully parallelize it. CPU are less efficient to do the same task. ASIC is the most efficient that you can get to because you can optimize it to as much as possible up to, well, the technology acceptable. So power, performance, area, PPA, you can optimize it. Of course, CPU, easier to design and debug because you just write code, made a mistake, do it again. You can find that. However, ASIC, difficult to design and debug because I'm talking about those minor details. You have to figure out, you have to have really good eyesight. There's some ways to get around that also with using very sophisticated software. And then debugging, well, once you produce it and you made a mistake, well, try again, find a mistake, and then produce again. So that's the problem with that. So you can see here, CPU are more flexible. You can program it more. GPU are second, okay? Um, then ASIC will be the most fastest, okay? Now I left over here blank because that's for the next topic, okay? So you can see, well, the benefit of CPU is programmable, okay? It's flexible. The benefit of ASIC is because it's using more parallelism, more circuit, so it's more hardware level, so I can speed it up. How about if we get the best of both worlds? We call it reconfigurable hardware, okay? So the basic idea is basically use hardware descripted language, a language like software or HDL. We can, some common example are Verilog, VHDL. So think of it as you do in C++, C, Python, all that stuff, but for defining circuit. You define your wires, you define your memory, all that stuff, and then you can load it to a CPU, sorry, FPGA. So how does it reconfigure itself? Well, the generic FPGA has this. It has logic blocks, interconnected wiring, and then also I/O cells. All of them are programmable. Let me get to the logic cell. So logic blocks has a bunch of what we call lookup tables. And basically, the lookup table, if you it has like a small memory inside, that basically whatever you put in the memory, it will self-reconfigure the circuit to be any circuit function you want. So an AND gate, an OR gate, an XOR gate, an NOT gate, a log, whatever gate. Um, then after the look, also it has a flip-flop that's a memory cell, a register. So you can have here to do the operation, your inputs, grab that, or you can store it, or you can just get it out if you want to get it to the next one. A bunch of this, like a bunch of them, are inside each block. And then if you want to communicate from here to here, each connection point has additional transistors, like switches. Transistor acts like switches, and it will turn on the path it wants. So for example, I want this path or I want this path, it will turn on and off the correct switches. How? Well, in the switch, because electrical, you put another memory cell on top, and then you put 0 or 1 on the memory cell to turn it on and off. Those memory cells, you can send it through USB, and then it will load your binary in there, okay? Um, So the circuit behavior is defined by HDL, or the hardware descriptive language. Logic is synthesized, like think of as compiling. So you grab your code, it synthesizes, and once it's synthesized, then it plays and route. So that means identify where is the best, like should I place it here? Should I place it here? Like for example, if I want to have a circuit that goes here to here, it's better than having to go all this long path. So you're trying to also optimize as best as possible. Once it implements, then generates a binary, and that binary gets loaded into the FPGA. Okay. And then you can also, at this stage, you can also get power consumption estimates. Any question of FPGA so far? So now, what is the difference between CPU and FPGA? Well, again, CPU runs software, hardware implements hardware designs. So as I said, you don't design necessarily a circuit. The circuit does not really change. It's just changing how it behaves underneath. Oops. The CPU is serial operations. FPGA, same as ASIC, is parallel and serial. CPU is less efficient. GPA also are more efficient. Easier to design, difficult to design, debug, but it's still much more easier than ASIC. Okay. So if I go back to ASIC and CPU, ASIC is difficult to design, expensive. However, FPGA is much more faster to time to market. What it means is it takes more time for us to start the designing up to the point of production and put it out in the market. So this is much faster. That means it's easier to code, easier to program, easier to debug, um, and other things like that. However, ASIC is much better power consumption because and area so on because you can remove the excess stuff to make it reconfigurable. Okay. Other thing is like FPGA are high flexible. You can make a mistake, go to your code, change it, doesn't matter. You have the chip, you don't have to reproduce it. It has high reproducibility, low time to market, as I mentioned. But however, the opposite is that compared to ASIC, ASIC is much more lower area than FPGA. ASIC has much more lower power consumption. So if your battery is what you're concerned, okay, you want to use more ASIC. Um, Also has a high volume production. So that means for the same dollar, you can produce a bunch of ASIC compared to FPGA. They're more expensive. They're like more than $1. Like one small FPGA like this size is like $75 and so on. And then you can get things in between. For example, you can see that here processor with FPGA, like remember I mentioned processors are very slow, so you can maybe add an additional FPGA next to it to kind of accelerate certain tasks of the processor. For example, a machine learning, you're trying to run machine learning in a processor, maybe it's faster if you just put it in an FPGA or in ASIC. Again, ASIC are harder to program, so you can do that. And speed up. You can see it has less, like it improves a little bit more. It's like a little more to the ASIC efficiency. Now, memory and storage. So to go over, there's different type of memory storage that you may have heard me mention a couple of them. So what is the main trade-off that you need to consider between different memory is that the read and write speed compared to the storage size and cost. Cost also includes the power consumption and also referring to how much you need to pay monetarily. Um, so that's the main difference that you need to consider. Either you want this more or you want this more. So registers are like literally on the top of the hierarchy. So in terms of speed, but they are much more larger and much more cost. So fast memory element, good for the CPU to do computation fast. Temporal, very high speed memory cells during CPU. So they're very good at what it does. However, you cannot just simply put the entire thing in registers because they take a lot of space. So if you want to have more instructions, you have to like use cells that are much more smaller, such as RAM. RAM, also known as random access memory, kind of for don't basically can you can it's a special memory you can access anywhere you want, and used for holding programs and data that are being executed. So it just holds it, but it doesn't do the actual computation. You have to bring it into CPU and then back. So they're high speed read, but not very high speed compared to registers. They're volatile. What it's saying for register, that means it voltage dependent. Once you turn off your computer, once you remove the power, it deletes that content. Okay. An example are cache. We often use what's called SRAM, and then main memory, which is often called we use DRAM. The difference is the SRAM is a bit bigger but faster, and then DRAM is much more smaller, so you can fit much more instructions. Okay, I'm gonna talk later about why we had two things. And then ROM, read-only memory. Don't look at the word read-only. It used to be read-only, okay? So it basically storage for a long-term storage. So if you want to save something for the long run. Also, if you want to turn off your computer, you can put it there. Hey, do you need something? Okay. Also good for transferring data or transferring data and storage, such as your flash drive, your SD card. All those are non-volatile. As I mentioned, non-volatile doesn't need power consumption. They're very low speed, very low. Okay, if it says read only, it's very low speed, specifically to write. Okay, so low speed to read, very low or impossible. So certain in the past, read-only memory used to be read-only. You cannot write to it. Now there's some more current ones. You're gonna say, well, if you're gonna have a ROM in your computer, you need to write to it. Now you can write and rewrite, but it's very slow. So example, hard drive, SSD, flash drive, EEPROM, etc. Now, well, We cannot just simply stick to one of them, and because you can see either very slow, but you can keep it, or very high speed, but it takes a lot of area, or very, very high speed, but has its own problems, okay? So what we do is combine them all. You can see, so we have here the CPU, okay? And the CPU has registers. So you can see as I go down into this pyramid, you can see how they get bigger, the size gets bigger and bigger and bigger, but also the time it takes, sorry, the size gets smaller, okay? So you can see this, you can only fit 16 bytes to 1 kilobyte in register. Cache, you can fit maybe 16 to 64 or 256 to 2 megabytes. You can see how the memory, you can fit more for the same area, okay? But however, you can see the time it takes is slower. So one cycle, this takes 10 cycles. This takes like 100 cycles. You can take a picture if you want to. I made this, so thank you. Or 1 million cycles, okay? It takes a lot of times. And then, of course, you can also add remote storage like cloud server, distributed system. That's in gigabyte, terabyte, picobytes, as large as you want to. Of course, slower read, lower you go, cheaper, more storage capacity. But um, and but will has less frequency use. Okay, so that means we try to avoid using this as much as possible. Like the CPU wants to use this as much. In some cases, if it doesn't have it here because they're small, you need to go to the cache. If it doesn't here, it looks in the second cache, in the third cache, in the memory, in the local, and then if in any case maybe in your remote servers like a cloud system. So it has a multiple step. If it gets, as soon as it gets a hit, like it finds the content, then it just brings it back up, okay? So that way you don't have to go through this slower. Mathematically speaking, they speed up, but you also have to consider how many cache you want. Some computer doesn't even have cache. Some of them only has one cache level or two or three cache levels. Of course, this will be the ideal situation of a very high-speed system, like maybe like a server or something like that. But however, as you get more smaller, maybe here you don't need this or you don't need certain things. You get smaller and smaller and smaller. So yes.
Like saving.
Well, these ones are not impossible, but you can write to them. But this is the time it takes compared to this one. So instead, it's not even 1,000; it's 1,000,000.
Like if you're typing.
And actually, when you write it, it goes here. When you're about to turn off, it will try to do it here while you're doing this. It will do this in parallel. But in reality, but most often, if you turn it off as it should be, you go to the settings, like you go into your actual computer, say, I want to turn off. It will grab everything your volatile memory and put it here, so you don't lose it. Okay, but sometimes some of the content here, sometimes in modern computing, when we go to multiprocessing, what we call dirty blocks. Basically, one block might have the content, but another block doesn't. So that way you don't have to like depend on each other too much. But then later, once you want to completely save it, then you have to like send it down. Okay, so you don't lose it. And sometimes, well, technically adding this doesn't have much, but you will have to have internet for this, which many devices have it. Any questions? Or did I answer your question?
So I think so it's like when you're making something and you don't save it and the computer just turns off, it's like it didn't have a chance to write to.
If that's why you don't want to force turning off, because it will do that. Same for a flash drive. If you take it out, it may not do it correctly, something like that. So it might still be connected somehow with something. Maybe still reading some data underneath, like passing back and forward some operations. So you want to always turn it off safely. So, and by safely is that way you don't lose data. Often, most computers immediately save it here, so you don't notice it, but it's still good enough. Okay, and there's some techniques to kind of speed up, like SSD are much more. I mean, it says 1 million cycle, but that's mostly because HDD, the hard drives, these are turning. But however, SSD are just circuits, so they don't have to wait for rotation. So they're much more faster. That's why they're much more expensive. Okay. Any other question? So register uses what we call D flip-flops. So basically, a weird way to do circuits so you can circuit bit into itself. But they're very big, like uses like a multiple circuits in a loop. But and they're very, very fast. However, this uses a different component called SRAM, which is basically two inverters like this and uses special math to figure out what is the bit. So this, because it's just two inverters instead of a bunch of gates, you can make it much more smaller. So it's like, this is like 6 transistors. This might be like 24 something transistors, 30 transistors. I don't remember, but something like that. Um, So they're much more larger, but they're very fast. However, this are a bit slower. You can only reach a certain amount at a time, things like that. And then more cache, more high chances you can do to avoid going here. Okay. Any questions? Any questions? No? Oh, okay. So future direction. So we talk about everything that essentially the computer. So future direction of research, one thing is neuromorphic computing. So if you remember from what I mentioned about CPU, the von Neumann architecture, you have what's called the von Neumann bottleneck. Every time you want to access the memory, you have to go through this single bus. Even though it looks like multiple wire, but in reality it's like 4 bits, but it's the same data, okay? So you can only go back and forth one, like read or like read from this or write to it. But you cannot do both at the same time. Certain techniques maybe to improve it, but it's complicated. So if you want to do like matrix operation, like multiple instructions at the same time, you can only do one at a time, okay? So what is the idea? Is that, okay, and also this is purely logic. So if you want to do more complex operations, you can only do mathematical logic, like addition, multiplication, something like that. If you want to do more non-linear, like maybe you heard the tangent. If you want to do tangent or sigmoid or cosine, you have in the computer lab you have to do like some weird technique with addition, multiplication to get an estimate. But we want to see if we can bring back the analog. Okay, so the idea is to use analog and parallel components. So you want to parallelize things, like imagine each of them are like smaller processor, like processing units with its own memory. So parallelize as much as possible. So these guys don't have, like this two don't have to work on this one. They can do it at the same time. Not only that, you can get analog because the idea is using mimic the brain, and sometimes you want something that's like the analog, like an analog function, you can use more like an analog component to do the math computation and other things. Maybe matrix multiplication. We're seeing if we can improve that since machine learning, this is a bunch of neurons. We want to see if we can improve it by using analog system. One of them is called MRES, press mem. It's like resistor, but like memory resistor. It's a bit more complex, but basically that's the idea behind it. So it's to mimic a human brain. There have what we call neurons. Each of those black box circles is a neuron, and you might see neural networks, and N. It's just a bunch of them together. And in CPU, you may have heard in regular software, machine learning and deep learning. You may have heard about them, but in the hardware side, we're trying to see if we can go from running it here in a simulation to see if we can bring it to a circuit level. That way we speed up everything. So since I mentioned about those neurons, what is a neuron in terms of hardware? Well, this is a neuron from the brain. So you have your many inputs, okay? Has what we call the nucleus. Oh, I was saying neutron. It's been 4 years I took biology. So nucleus and then the axon is just a path, like think of it as a wire, and then it has the output to connect to the next neutron, like this, okay? So in the same way as an artificial neuron, this the dendrites, if I said it correctly, your inputs, you have here your inputs. Um, this does something called multiplication. It will multiply and add. Okay, so the multiplication is basically a weight. These weights are a what is being learned when you do machine learning. Only that's being learned. So you multiply and add. So the one before you multiply, add, multiply that. This is just a sum. Okay, and then that sum go to an activation function. Okay, and the activation function could say, oh, more than basic binary. Is it higher than this? Turn it 1. Is it lower than that? It's a 0. What happened? Oh, okay. So that's where the function can come in and say, well, if you do it mathematically computational, then you have to do those logic. But often this function tends to be hyperbolic tangent, which is, or sigmoid, which is more like an S shape. So that where we can get the analog side. So if you grab a bunch of them, let's say each circle is a connection, you can see let's grab this one. You can see from the previous layer, it connects all the, the neuron from the previous layer into it. And each of them will have its own weight. Same for all of them until it reaches some expected output. Okay? So the connections, the synapses, like similar here, is this part, all those connections. And the previous layer connects to all the next layer, and that layer connects to the next layer, and so on. The only thing that, as I mentioned, only thing is learning is the weights. So you put a random weight, pass it through. Is it correct? Good. Is it incorrect? Then it does something called backpropagation. It's a bunch of mathematical stuff, and it would replace those values with the next potential step, and using like gradients, derivative, integral, things like that. Mostly, well, not that much integrals. It takes small steps at a time. You put a lot of data one at a time. It's making small step until it reaches an ideal weight or close enough. There's always a margin of error with so much data. Um, so the data neuromorphic, you go from digital computers. The brain, it has, you can think of each neuron like, oh, it's like a bunch of different computing with different synapses, different memory cells. So instead of using software, you can mimic these connection points using this hardware level neuromorphic computing. Okay. Although they kind of being simulated nowadays in purely CPU. They're still working on getting this more hardware level that's much more faster. Um, what is the difference? This is using purely binary signal. This is the brain uses spike signals. Well, how about if it continues using spike signals, the analog part? Okay. The device. Well, this is your regular CPU, gates, memory. However, this is unknown. Sorry, no. It's a biological neuron synapses. This will be the artificial neuron synapses in the hardware level, ideally. Okay. How this learns uses programs and logic. This using learning algorithms. We had no idea how the brain learns yet, so hopefully we try to mimic this as in the future as close as possible. Any question about neuromorphic? Oh, I didn't put an intermediate slide, but Greg, this is the last topic, quantum computing. So I just want to give you an overview. The idea of quantum computing is that it's basically a quantum computer, our system that harnesses the collective property of quantum states to perform computation. Why is it quantum state? So if you want to quantum particles, one example will be a neutron, okay, of light. It's basically any particle that's very, very small, okay? They will have what is called quantum states. For example, in the case of a neutron, or electron, sorry, you may have her electron spins, okay? Those are quantum states. You can have spin up, spin down. Basically, if you spin this, well, it doesn't really spin, but it looks like it's spinning mathematically. But basically, if it's spin one way, we call it up. If it's spinning the other way, we call it down. It's not truly spinning, but you can pretend it is. So that gives you how many states? 2. So you can represent 0 and 1, something like that. So you can do your binary with those. However, the great thing about quantum states that, oh, also there are more quantum spin, electron spin, atomic spin, photopolarization, the polarity of a electron, sorry, of a light, all that. But the thing is, it even though it has two real states, you can superposition them and such that you can have like an intermediate state. But when you read it, you can only read one or the other. So it will collapse into either up or down. Okay. So that's the part that seems like, oh, the confusing part, like how it can be both up and down. It's just in between. Okay. It's just when you measure it, you can only measure one. Okay. That's when it collapses. And more other mathematical computation behind it. So that's superposition, interference, and then also entanglement. Like you can tangle one quantum state with another quantum state, send them very far apart, and you can turn this one on. Like say this is going to be one, then you can send the other side very far away to the moon, for example, a spaceship, to turn it back zero, like almost immediately at the speed of light. So you can do that for transfer information. Okay, like communication. So what is the thing? New mathematical real for current computers. So you have to change how we do math in computers. Instead of using basic binary, basic stuff, you have to use more quantum computations. So for binary to complex matrix. So now it's not just ones and zero, we have complex numbers, like a plus bi, if you see complex. And they're not any number, but vectors. So you're not only using just number, it's a vector. Expand the computer operations so you can do more of those. Different bit circuits and components. You have to use more quantum elements to do the read the quantum elements, all that. New way of communication, which is entanglement I mentioned. And then new ways to storing data, which is superposition. So instead of just having a memory cell only be up and down, you can have storage of anything between, which is gonna touch here real quick. So improving speed and storage, okay, and capacity. So classic 2 bits are 0 and 1. Originally used two-state DC voltages, so either high or low. So limited space, speed, power, energy. So that memory cell is there. However, so you can see 0 or 1. That's only you can have in a regular classical bit. Classical will be referring modern computers. But the quantum bit, also known as qubit, quantum bit, you can see either you have 0 or 1, but before you measure, you can have a superposition. So it can be in anything between in 3 axes, x, y, z. So not only it's like one dimension, you can have 3 dimensions of different values. And you can see and when you measure, you either measure 0 or 1, but at least you can store data of anything between. Okay, so you can think of it as both 0 and 1. So qubits are superposition of 0 and 1 and anything in between. Use quantum particle superposition states. One qubit can represent 2 bits because you can store something in between. So you can think of it as if you want to replace every 2 bits, you can replace it with 1 qubit. So you can see if you have n qubits, you can substitute n to the power n bits, approximately. So you can see it's an exponential improvement. So a lot of modern a lot of current algorithms has a lot of very high time and space complexity that exponential is basically impossible. So if you have exponential improvement, hey, maybe you can solve many NP hard problems. Okay, it's missing the hard, which can basically solve a lot of issues. For example, one thing you can think of is crypto systems to secure maybe your credit cards, a lot of your passwords, all of that. Uses complicated non-polynomial time, like NP problems, very complicated, such that you cannot compute it with any computer, even if you have the entire time of the universe and many computers. You can't. Okay. However, if you have this exponential improvement, you can break those. That's why don't worry. There's a lot of challenges. You already reach a conclusion of what quantum computing after we come to computing algorithm. Once we get to the future into quantum systems, we have reached many candidates, and some of them already won for certain tasks. So um, things like that. So don't worry, you're secure. People are still working on that. Okay. Um, Now, how we represent the state is that we just 0 and 1. We use something called qubit. We use something called the shooting equations, or the wave function. Okay. So how is represented? So remember the zeros and 1. This is how we represent it. So this is a vector. A vector 1, 1, 0 will be represented as 0. So this guy. And then a 1, which is 0, 1, will be this guy. If you can do some arithmetic, let's say this guy plus this guy, you can have a new vector like that. Okay. You just need to change the value of a and b, and you can get anything in between. So okay. So if you put 0 for a and 1 for b, okay, then you will get this state. If you put 1 for a and 0 for b, you will get this state. Okay. And then if you put anything in between, you will get anything in between. Not only that, you don't need to only use real numbers. You can use complex numbers. So you can even have imaginary numbers in there, which add you the additional dimensions. So, which is great. So these two add you only 2 dimensions, but having the complex number give you 1 more. The only restriction is that because this is the wave function, when you it needs to be, when you do the Pythagoras theorem, basically a squared plus b squared must equal 1. The reason is when you square each of the numbers, it gives you probability. So what this number represents probability of being a 0 compared to a 1. Okay, the higher a is, the more probabilistic you can. It will be it will be a 0. Higher the beta, it will be 1. So the probability, a squared probability of a plus the probability of f of 1, which is beta square, it must equal 1. You cannot have more than 100% or less. So we know those are the only 2 conditions, final conditions. Which one it is in total is 1. Any questions about this? Now, here's the limitation. Great, sounds okay. I think, yeah, that was the last slide. So yeah, so real quick, so limitation. Quantum computers are limited by many errors. So basically, any noise, faults, loss of quantum coherence, anything can damage the computations. So caused is by vibration, temporal fluctuation, electrical wave. So anything of that can make it the detection, and the clock, and then collapses it down. This can destroy or collapse quantum states. Okay, so you will lose the superposition. Quantum state has short lifetime due to this error, so that's why you can only do a computation one time, and then that technique, if you bring it to classical computer and then bring it back, classical back. That way you don't completely loosen, because any of this error can, well, it will kill it. Data transmission to quantum entanglement are not renewable, because you need to entangle it here and then send it. So once you send it, you cannot you will need to bring it back to entangle them again. So it's like non-removable. Like it's not like I can call you, can talk to you, but it's not like I can continue talking to you. So that's why we say non-removable. That other person will have all those quantum particles for eventually until they just have it back. Okay. Um, Quantum computers are too large, expensive for average consumers. The only current computers are like in Google. I think it's called IBM. They also have one in their systems. They're very large. Only big companies can have it, but they're using it for research purposes. But if you want to play with them, there's an accessible remotely. You can remote the actual IBM quantum computer. You can use that, and you can program a small cell bit, like 4, 5 qubits, something like that, small circuit. You can do that remotely. Okay. So if you ever use Google Colab, something like that, which connects to the Google servers, it's similar here, but for quantum computing. Current quantum computers have very small computation capabilities. Oh, sorry. I thought I was reading this one. It only has a small operation. So the thing is, the set of instructions you can do is very limited. So in classical computers, we have NOT gate, AND gate, OR gate, XOR gate. This has much more less. So you have to, if you want to do more complexity, you have to have more of those gates. And then due to cost and error of classic of those, then we try to use classical computer as much as possible. Now, even though if you reach the very good quantum computing, it's still going to be way more efficient for a task, an everyday task. Okay, so if a task that can do very well in classical computer, continue doing classical computer. Just you only use quantum computer when you need to get out of that realm. So only useful for large complex algorithms such as optimizing problems, that data analysis, and certain simulations.